Hey, how's going on everyone? Welcome to the new video in our Algorithms Design and Analysis series. Today we will discuss some asymptotic notations in detail. First, we have the big O notation. The big O notation gives us the upper bound of a function. The big O of g of n states that for a function f of n, there exists positive constants c and n naught such that our f of n is greater than or equal to 0 and is less than or equal to c g of n for all n greater than n naught. Let us understand this better with help of an example. Let's say we have a function f of n which is equals to 3n square plus 2n plus 1. Now we want a function g of n such that c g of n is greater than or equal to our f of n. Let us take 10n square. To verify this inequality, let us substitute n with 2. On our left hand side, we have 3 times 4 plus 2 times 2 plus 1, which is equals to 17. And on our right hand side, we have 10 times 4, which is 40. As 40 is greater than 17, our inequality is verified. Therefore, we can say that f of n is the big O of n square. What if we took another function instead of 10n square, such as 6n cube? Again, by substituting n with 2, we would have 6n cube equals to 48, which is again greater than 17. Hence, our f of n is the big O of n cube. Both of these statements are correct, but we consider the n square because we want a asymptotically tight bound, which means that we want a function which is closest to our f of n. Understand this graphically. Let's say we have a function f of n whose graph is represented by this line. Now for f of n, we have a function g of n such that c g of n is greater than or equal to f of n for all n greater than n naught. We might also have another function d h of n which would also be greater than or equal to f of n for some values of n greater than n naught. Here f of n is the big O of both the function g of n as well as h of n, but we consider g of n because we can see that g of n is closest to our f of n and we want a closest bound. So we say that f of n is the big O of g of n. F of n is also the big O of h of n, but considering the closest bound, we are saying f of n is the big O of g of n. Next is the big omega notation. The big omega notation gives us the lower bound of a function. The big omega of g of n states that for a function f of n, there exist positive constants c and n naught such that f of n is greater than or equal to c g of n, which is greater than or equal to 0 for all n greater than equal to n naught. Let us again understand this with help of the same example. F of n is equals to 3n square plus 2n plus 1. Now we want a function g of n such that f of n should be greater than or equal to g of n. Let us consider 2n square. Let's verify this inequality by substituting n with 2. We just saw that on substituting n equals to 2, our left hand side evaluates to 17. On our right hand side, we have 2 times 4, which is 8. As 17 is greater than 8, therefore, we can say that f of n is the big omega of n square. Again, we could have chosen another function such as 2n instead of 2n square. F of n would also be the big omega of n, but we choose the asymptotically tight bound, which here is n square. This is the graphical representation of the big omega notation. We have a function f of n, and for f of n we have another function g of n such that c g of n is less than or equal to f of n. Again we have another function d h of n which is also less than or equal to f of n for some values of n greater than n naught. And f of n is a big omega of both h of n as well as g of n, but we consider g of n because g of n is the closest function to f of n. Now we have the theta notation. The theta notation is the most important notation of all three and it gives us the average bound of a function. The theta of g of n states that for a function f of n, there exist positive constants c1 and c2 and n naught such that c1 g of n is greater than or equal to 0 and is less than or equal to f of n, and C2 g of n is greater than or equal to f of n for all values of n greater than or equal to n naught. Again, we will consider the same example. F of n is equals to 3n square plus 2n plus 1. We just saw that our f of n is less than or equal to 10n square and is greater than or equal to 2n square. This inequality was just verified and it also satisfies our definition of theta notation. Here C1 is equals to 2 and C2 is equals to 10 and g of n is equals to n square. Therefore, f of n is the theta of n square. What if we took 2n instead of n square? F of n would not be the theta of n because for no value of n, 2n would be greater than or equal to our f of n. Similarly, if we took 6n cube instead of 10n square, f of n would also not be the theta of n cube because for no value of n, cn cube would be less than or equal to our f of n. Therefore, f of n is the theta of only n square. This is the graphical representation of the theta notation. We have a function f of n, and for our f of n we have a function g of n such that c1 g of n is less than or equal to our f of n and c2 g of n is greater than or equal to our f of n for some values of n greater than or equal to n naught. Till now we have discussed the theta notation, the big O notation and the big omega notation. Now out of all these three, the theta notation is the most useful and the most important notation because the theta notation gives us the average bound of a function. From theta notation we can determine both the upper and the lower bound of a function, but sometimes we are not able to find the theta notation. So we use the big O notation. The big O notation gives us the upper bound of a function. The theta notation and the big O notation are used most commonly, but the big omega notation is not used frequently because it gives us the lower bound of a function. Now sometimes people confuse the big omega notation for best case, the big O notation for the worst case and the theta notation for average case analysis. But it is not true. Case analysis is totally different from asymptotic notations. We can represent any case with the help of any of these three notations. Apart from those notations, we have some other notations as well. One of them is the small o notation and another is the small omega notation. The key difference between the big O and the small o notation is in big O, we prefer the closest bound, but in small o, we do not consider the closest bound. We ignore the closest bound. In its definition also, we say that our f of n should be less than cg of n, should not be equal to cg of n. Similarly, in small omega notation also, we ignore the closest bound, which is represented in definition also. Cg of n should be less than f of n and should not be equal to f of n. That's all for this video. In the next video, we will discuss some properties of these asymptotic notations. Thank you for watching this video. If you like this video, please give it a thumbs up and share your opinions in the comment section. And do follow us on Instagram and Twitter.